So as with the lectures on timber, steel, and concrete, this lecture is not exhaustive, but really an introduction to bricks, block, and stone, otherwise known as masonry. I'll cover the same I'll use the same sort of pattern to cover this as I have with the previous materials, with previous lectures, and the source for this mostly has still come from Ken Ward Harvey's Fundamental Building Materials. Okay. So what we'll do is we'll look at these four things. Actually, I am going to plan B it and get rid of number 4 because we're not actually going to do that. Okay. So we'll look at stone, traditional, which is a traditional form of masonry, and followed by bricks and block work, or bricks and brickwork rather, which was also very traditional, but perhaps not as old as just finding rocks and piling them up. And then on to blocks and block work, which really refers to concrete blocks. So I will touch on the thermal properties of materials, but remember that this stuff is all going to be covered in different units in your second year, so we won't really go into it. Now, if we go to the next slide, this will look familiar to you because this is the heading page, I suppose, of the things that we've looked at with all the materials that I've talked about this semester. Stone's density ranges from 1,800 kilograms per meter cube to 3,000 kilograms per meter cube. So you'll notice that it's lighter than steel, heavier than water. It will sink in water. Also, it has a similar kind of strength to concrete, similar density to concrete. The compressive strength ranges from about 38 megapascals to 180 megapascals. So the weaker stones are actually about the same compressive strength as timber. Now, of course, the range has to do with the type of stone, whether it's a sedimentary stone or some sort of metamorphic or igneous stone, which we'll go through in a minute. Now, tensile strength is not very good at all, starting at about 18 megapascals and going through to 65 megapascals. So similar to unreinforced concrete. But of course, there's ways of getting around this, which I'll talk about in a minute. The moisture, again, it varies depending on relative humidity and also the porosity of the stone, and can be up to 5% or more, depending on whether it's exposed to water or not. And the characteristics similar to concrete in that it's best in compression, in fact very good in compression, but quite limited in tension. Of course, in terms of concrete, we do have steel reinforcing to make concrete work better in tension. With stone, you can see on the slide on the bottom here, which is an ancient Egyptian building. You can see these kind of stone beams here. The reason why these columns are this far apart is basically got to do with the strength of the stone. If the columns are any further apart, the stone beams would break. So this was a kind of trial and error method that they used to achieve the maximum spans of stone. The ancient Greeks used a similar formula. They had better technology in terms of carving surface decorations and what have you, but really the fundamental strength of stone didn't change because the technology was the same. It wasn't until the Roman times when the invention of the arch, as you can see on the slide above, with the invention of the arch, the shape of the way stone was laid then allowed for larger spans. So you can see here that these spans here are actually larger than these spans here, and some quite large brick spans could be made depending on the configuration. So this is actually a Roman aqueduct where there was a channel on the top used to bring water from the mountains down to the towns, and many of these structures still exist, which is testament to their technology and their construction. Okay, moving right along. If we now look at how stone is quarried, how stone is sourced, I suppose. So we'll start with granite and basalt. So basalt is also known as bluestone in Australia, but basalt is found all over the world, as is granite. So what you can see is that it is quarried. There's a big lump of it, like several thousand cubic meters worth of it, cubic kilometers even of this stuff. In certain spots based on certain geographical and geological histories, and us smart humans have gone in to chip it out. So you can see different kinds of stone are chipped out in different kinds of ways. The basalt on the top here tends to fall apart according to certain seams, and that seems to be the way that they can get it out. Whereas with granite, it's much easier to get out large blocks of it. All right, so and you can see the scale at which it's done. You can see these little tractors here and these little humans. So it's quarried on a massive scale, as is granite. So, what are these two materials? So what we've got here is a smaller sample of basalt or bluestone on the top, and a smaller sample of granite, which you see on the bottom. Now, both basalt and granite come in a range of colors. There's much more different colors of granite than they are of basalt. And they are cut down to big blocks, from which they are then further cut down into different sizes to be used. Now, I've kind of lost my way a little bit, but what we have is that, what we have is these two kinds of stones are called igneous rock, granite and basalt, and they are created through volcanic action. So when you've got a lot of volcanic action, a lot of molten lava and what have you, the heat and the pressure actually creates this kind of rock. Okay, so it's formed by the crust of the earth, essentially. The other kind of stone is really what's called metamorphic rock, which is the example you can see here of marble. And marble is quarried in the same way. These are the famous marble quarries of Carrara in Italy, but this kind of white marble with the grey streaks through it here is also available in quarries in Iran as well as in China. And metamorphic rocks are basically start off as different kinds of rocks. They start off as limestone, which is quite a porous and lightweight rock, which is when it is exposed to high heat and pressure. For example, when you have a volcano which decides to erupt next to a seam of limestone, you end up with marble. So you can see that this kind of metamorphic process is really unbelievably powerful. If you can have a look here, the amount of marble that was all one lump that started off, you can see the amount of heat and pressure that was necessary to create it. So needless to say, all these kinds of geological actions were not taking place in a large scale when humans were around. Otherwise, yes, it's hard to imagine that this would be happening when humans were around. But on the same note, you can see like these large blocks of Carrara marble, which are almost 2 stories high, which are cut out as big lumps, which can be cut out as big lumps because this kind of metamorphic rock is actually softer than granite or basalt. And then finally, we have what we call sedimentary rocks, including limestone and sandstone, which are formed really by a very long, slow process of sediment being deposited at the bottoms of rivers and creeks and what have you, and over time, the whole lot being compressed down to being a kind of rock. Sedimentary rocks are the softest kind of rocks, and as you can see with the image on the bottom, can be much more easily cut. In this case, just a big saw on the end of a big digger thingy. Digger, that's a technical term, by the way. Digger thingy can actually cut out big blocks of it. Whereas with things like marble, is a bit more difficult. They also use saws and what have you, but with bluestone, quite often they have to sink in a number of drill holes to which they have little explosive, which then kind of blast bits of rock off. Okay, any questions so far? Very good, because I'm no geologist. But if we move on to have a look at what sandstone and marble look like. So on the top here, we've got marble, which is a metamorphic rock, and sandstone, which is a sedimentary rock. This is the way we generally use them. So nowadays, they are mostly used as cladding. So they're sawn into slabs which vary in thickness from 30 to 60 mil, depending on the size. And then they're used as actually as a facing for architecture, for benches, for buildings, and so on and so forth, also for cutting boards and pavers and so and what have you. Same thing with sandstone, as you can see down here. Sandstone, you can see this amazing grain that it has, which is really the different layers of the sediment settling on the bottom of rivers and what have you. And the reason why it curves is later when geological activities happen, which change the kind of shape of or the grain of the rock. Now, these stones are, when they're used, because they're used mostly as veneers, they're covered by 7 different Australian standards, which I won't go into here, but just to say that they are standards to do with how they're graded, they're cut, they're polished, and so on, and measured, and so on and so forth. Traditionally in Australia, these kinds of stones were used structurally to build buildings. So as load-bearing blocks, both as you can see on the left and on the right. And nowadays they're still used structurally, but mostly for infrastructure, meaning more for roadworks and retaining walls and dams and what have you, and not so much for building structure, where it tends to be used more as a veneer. So on the left we see an example of a bluestone church in Port Fairy in Victoria, and these walls down here are really quite thick, and they get thinner as they go up, so they taper on the inside. But you can imagine the stone down here, which is taking all of this load up here. It demonstrates the abilities of basalt or bluestone in compression. Another example is Walter Burley Griffin's Newman College in Parkville of 1918, which is made out of Sydney sandstone. Now, I think Griffin had a particular liking for sandstone as a material, so he actually had all the sandstone shipped down from Sydney. Sydney sandstone shipped down to Victoria to build Newman College. Perhaps he didn't like bluestone that looks a bit more like this. Now, stone is good in that it is it can be relatively waterproof and fireproof. It has very good acoustic damping properties, so it will cut out the sound from outside the building. When you cut it into blocks, it's pretty easy to join with mortars, with old-fashioned and new-fashioned mortars, and it generally weathers well. Now, I might say that in the case of Newman College, this hasn't quite been the case, because if we go back to this slide here, the way you're supposed to lay sandstone is like this, with the layers going horizontally. But for some reason, Newman College, the layers were actually laid vertically, which meant that the water was able to start to degrade the different layers which has led to a very expensive and long a restoration process, which has been overcome, and the problem has been overcome with modern very expensive sealants which don't look like they're there. The disadvantages before I go into disadvantages, there's many ways of using stone, which is another advantage. It can also be used as aggregates, which I've talked about in the concrete lecture. So when you grind down the concrete, you get all the colors of the stones coming through. And it can have good thermal qualities because it has got thermal mass. But you do need to keep up the ambient heat that you want it to be at, or cool. Otherwise, it's going to just try to be the same temperatures outside in due course. Again, this is not really important for this semester, just to let you know that these things are considered. Disadvantages. It's difficult to quarry relative to collecting timber from trees. It's heavy. You need machineries for larger blocks. They can be uneven. They're more difficult to shape relatively, and some stones degrade faster than others, such as the sandstone example I've just spoken about. And stone is also subject to degradation when exposed to acid rain, which is really got to do with too much burning of fossil fuels, which gets into the rain. It was a problem that was most prevalent in Europe in the 1980s and 1990s, and now is starting to be a problem in places like India and China. Now, so moving right along, what I might do is give you another few examples of how stones are used. This is a very figured form of marble that has been used in the Barcelona pavilion, which of course is in Barcelona in Spain, originally built in 1929 and rebuilt in 1986. So this is the rebuilt version. So what happens here is that stone has or marble has a specific noble association, if you like, and it's used here as a veneer to denote that this is a special building. So really by the early 20th century, this kind of material was already being used as a veneer rather than as a base construction material. In common usage, it's mostly used as retaining walls for infrastructural use, as I said before. What you see on the top there is a form of slate, and on the bottom basalt, which is put into steel cages, which are called gabions. They are also used for very rustic stone walls, and you can see a lot of these kinds of things around Canberra with the beautiful yellow, brown, red sort of Canberra slate. Is it a slate, Gary? Shale. So it's a lightweight stone, but this is the local Canberra stone is that kind of yellowy, reddy, browny color, which is quite beautiful when you make it into stone walls like this. Also, quite often stone is used for paving, and it can be installed on lightweight or solid substrates. So what a substrate is the material that sits underneath your paving. If you were noticing that diagonal path with the crushed granite, compressed crushed granite sand topping beside the library, going from the library over to the well, the substrate there was really some sort of gravel, some sort of bluestone gravel, which was really hammered down before they put the granitic sand on top to hammer that down. So in these cases, quite often they're laid on a concrete slab, but otherwise they can also be laid on really what you call stabilized sand, which is a bit of cement mixed into the sand to make it a bit harder. Okay, any questions on stone before I move on to brick? No questions, very good. So, the second thing I'd like to talk to you today about is bricks and brickwork. The density of brick and brickwork is about 1,600 kilograms per meter cubed, so considerably lighter than stone, but with a very good compressive strength of up to 80 megapascals, depending on the clay and firing. So of course, you can, from that comment, you can then tell that bricks are made from clay and need to be cooked or fired in a kiln in order to achieve their ultimate strength. And the firing or the cooking of it turns it from a plastic malleable clay into a brick, which is very hard and has a different structure and is completely unelastic and quite brittle. No one bothers with testing the tensile strength of brick because it doesn't have any. Well, not to say it doesn't have any, but it's very limited. Brick is porous, so cooked clay is porous, same like stone, and it's best in compression. Now, bricks, of course, can be made into many different shapes and sizes. And in Australia, they are covered by 9 Australian standards to do with their manufacture and so on and so forth, and standard and quality control and what have you. But the standard size for brick in Australia is 230 millimeters long by 110 millimeters deep by 76 millimeters high. By and large, you're going to find that this is the standard size of a brick across the country. In the 60s and 70s, around the time when the metric system came into Australia, a new dimension for bricks came in called the metric modular brick. And the metric modular brick is something like 400 or 390 by 90 by 90. Okay? So what we can see on this wall here is a standard Australian brick. But what we can see in the rest of the campus, especially out around the hub and so on and so forth, and the library and also Building 7, is the metric modular brick, okay, which is narrower and longer. So we have both standards in this campus, which is good for us. So what I'd encourage you to do is really to, as with the stone, is to, in your travels around every day, to try and identify these things as you come across them. What kind of stone it is, what kind of brick it is, and so on and so forth. So bricks are made from clay, and more recently we have had bricks that are made from concrete or a mixture of cement and earth. So clay is a soft plastic material, and it's quarried from seams of clay that you find in the ground, as you can see from the picture below. And it doesn't have the clay does not have a directional grain, but clay is famous for being able to hold on to water. So what happens is that you need to actually compress the clay to get rid of all the excess water in the clay before you form them into bricks and fire them. So on the top 2 images, you see a couple of pictures I got from the Austral Bricks website, which are really what happens to bricks on the right when they come out of their kiln. You remember the big kiln, the oven-type kilns that I showed you when we were talking about timber? Same thing happens with bricks, except at a much higher temperature. Okay, so essentially, what you see here is formed into brick-shaped type things like this, which are then left to dry for a certain amount of time and then cooked until they get nice and hard. So really, clay is good because it can be formed, but in its uncooked state it's not useful for very much. Now, this technology is not new. It's been around for quite some time. And if you look back to other things that are made with clay, like ceramics, so bowls and jars and what have you, and these kinds of firings have gone on since prehistoric times. So this technology is very much not new. Nowadays, all we have is that we have a better way of actually controlling the process. So there are 2 different kinds of bricks. The first kinds of bricks are pressed bricks, where you get your semi-dried clay put into a mold and stamped out. You can see this one, which is a Melbourne City brick with the M in there and the word city on it. And around Canberra, you'll see very many bricks stamped Canberra Commonwealth. So we do have a local seam of clay appropriate for making bricks, and the old brickworks in Yarralamla was where they used to be made. This is the preferred type of brick traditionally, because what you can do is you can actually key in the hole here, which then gives it a more purchase when you're actually stacking them up, and gives the mortar something to grip on, so that you can actually so that the wall will be stronger. The other type of brick is what you call an extruded brick. So essentially it's pushed through a mold, a brick-shaped mold, and then they use a wire cutter to cut it exactly to the height that is required. The top two versions are kinds of extruded bricks that we might find in Australia. This one I was thinking was quite uncommon until I looked at the brick that I'm using as a doorstop, and it's exactly this. But there are many other forms of extruded bricks like these ones here, which they use in Europe and also in certain parts of Southeast Asia. I think this is a French tradition, because this is how they make bricks in Cambodia. So really the conventional use of bricks are for houses, for cladding, for fences, and so on and so forth. You can see that all of these things work best in compression, and when you have these kinds of corners here, what you need to do is you need to support it with something else. Okay, so nowadays we have steel lintels to be able to hold up flying corners of brick. But in the old days, they used different ways, different methods, which I'll get to in a tick. So what's good about brick? Brick is really good in compression. It's very long-lasting. Lots of ancient examples still exist today. It's a very low-maintenance material, and it's got this particular particular way of failing structurally, which is quite fascinating, where basically it will fail along the mortar lines, and one brick will transfer it to the next brick, transfer the load to the next brick if you've got a stretcher bond, a normally sort of overlapped way of laying bricks like you see on this wall here. So what happens is you can remove the whole corner of a building, and the building will remain standing. Okay, and this is a case of a sinkhole that opened up in Sydney about 2 or 3 years ago when they were building one of the tunnels there. Sinkhole basically is uncontrolled. It's a hole that's opened up by the uncontrolled flow of water. Okay, so once you get a lot of water in there, if you have no control over it, it just erodes away the earth, creates a big hole, and the corner of your apartment starts to fall away. But I thought this was quite amazing that certainly in this case it's the concrete slab that's holding up this corner, but what's holding this up is actually just the loading on the brick actually being transferred down to a different part of the footings. Now the other good thing about bricks is that they can be recycled. And so when you have a brick building that's being taken down, what you can do is employ a brick cleaner, which is like the chap on the bottom, using a brick hammer and a brick chisel and various other tools. You can then kind of chip all this excess mortar on the bricks off in order to be able then to recycle them. Now the recycled bricks, of course, have their own particular texture, not a bad texture, I think, as you can see with this example of the House of Two Architects in Fremantle, made completely from recycled bricks. They do have quite a beautiful texture to them, not to mention reusing something that will otherwise end up in landfill. Now, the bad thing about brick is that it's no good in tension. Although, like stone, you can overcome it by using arches to basically transfer the loads to the ends. In this case, the flying buttresses of a church, and in this case, an aqueduct like the stone one I just showed you, but done in brick. So, what's bad about brick? Well, It's porous, so when we build it now, if you don't build a thick enough brick wall, then the water will be able to get through and spoil your wall finishes on the inside. It can also suck up water from the ground in terms of capillary action. So you need to have damp-proof courses to stop the water from actually crawling up through the bricks. It is also heavy, and needs a lot of energy for manufacture and moving. In certain circumstances, the bricks can get eroded, like when you've got a lot of moisture and a lot of salty air, like marine type or beachside type environments. You need to make sure that your bricks are properly fired. Otherwise, the surface of the brick, which is harder than the inside of the brick, can start to get eroded. And also, with older bricks that were fired under with less heat, they're not quite as hard. So even in Australia, the bricks that were made in the late 19th century were little more than kind of sun-dried bricks, I think you'd say. So when you're looking at 19th century buildings and you poke your finger in a brick, if it crumbles, that's okay. That's just what it does. Bricks have been used for lots of interesting architecture over time. In the modern period, one of the most famous exponents of brick was the American architect Frank Lloyd Wright, who worked out of Chicago. I had a big office there, and he designed a lot of brick buildings. Including his Roby house of 1910, which is a kind of funny thing because it sits in the middle of an older suburb. But when you go to Oak Park, that's really a very interesting place to go because it's full of houses that came out of Frank Lloyd Wright's office. And of course, one of the most interesting one was a house that was designed by Walter Burley Griffin when Griffin was working for Wright. Down the bottom, you can see the Morris gift shop of 1948 in San Francisco. This was a prototype of the later Guggenheim Museum, as there's a kind of curled ramp inside. But Wright was very much using the properties of brick in order to achieve certain structural ends in employing the form of the arch. Wright's architecture was very influential. It could be argued that without Wright's Fasteners portfolio, which was a portfolio of Wright's drawings going to Europe in the early 20th century, that these buildings could not have been created later on. For example, the Hilversum Town Hall of 1931 by Judoc in the Netherlands, and later Louis Kahn's amazing buildings in America and in India on the bottom. So Kahn was another great exponent of brick. He had an almost spiritual sort of conversation with his materials. So he was famous in the Yale Architecture School for picking up a brick and asking it what it wanted to be before he came up with these amazing designs. I never quite got that, but never mind, it's a good story. And then more locally, I think you can see a lot of really a lot of brick buildings in Canberra, especially with the older houses and older apartments. So we have a very strong tradition of brick construction in Canberra. I mean, there were buildings like Old Parliament House that was made of brick and then rendered and rendered over and later painted. But you can't really see the brick. In cities like Melbourne, especially in Melbourne, there was a tradition of brick being used as a high-rise cladding material. So we see the gas and fuel buildings on the left by Parrot Line Matheson, demolished 1997 to make way for Federation Square, and then the quite amazing Royal Melbourne Hospital buildings on the right by Stevenson and Turner, completed in the 40s. Brick is still very current today. We see the new Tate Modern building by Herzog and de Meuron that opened last year. That's made out of brick. Right now, brick has, of course, become more of a cladding than a structural system, because all of this would have been panelized and lifted up to be hung off a concrete frame. an interesting example of brick which defies its traditional structural properties on the right. The Harold Street house by Jackson Clement Barrows of 2013. Really, you can see that bricks here have then been employed for their porosity as much for their solidity. They're used on first floor levels, on cantilevered corners and what have you. And of course, all the structure for this is no longer brick, right? The structure is actually carried by other things. So finally, we talk about blocks and block work. So as I said before, when we talk about blocks and block work, really we are talking about concrete blocks. And block work, of course, are walls of concrete blocks, or concrete blocks that are joined by mortar. The density of concrete blocks is much lighter than bricks or stone, and that's because they can be made to be quite hollow. And you can see that they don't have a lot of strength, but in terms of modern construction where something else is taking the structure, something else is taking the load, you don't have to worry too much about strength. It has a bit more tensile strength, but still it's really not meant to be used in tension. So we have quite a lot of concrete block around as well. So if you're walking from here back to the studios, the big long corridor that you walk down after the water fountain on level B of building 7, just as you go in from there, that whole building, the interior walls are all made of concrete block, which has then been rendered and painted. So your standard concrete block is 290 by 90 by 190 high. So those are exactly the ones that you see in that corridor and round the corner to the glass bridge. This is what they look like. You can actually get solid ones, but most of the ones that you get are hollow like this, with the wider versions having bigger holes in them. These do not require cooking. So like any cement product, you mix up your concrete, you put it in a mold, and you wait for it to dry, and after a certain amount of time, it reaches its maximum compressive strength as per the lecture on concrete. It's mostly used as building material for domestic architecture. There was a lot of modern houses in the 60s and 70s were built out of concrete block, where really the idea was to leave everything exposed as part of what you might call a brutalist approach to architecture, which I've explained about when we were talking about concrete. And this is probably the most famous example, the Heidi II house in Heidelberg, which is now part of the Heidi Museum of Art by Michelangelo and Everest. And it remains a material of choice for architects who have clients who have not a lot of money. This is an extension that I did in Adelaide, where we've used the blocks exposed. And actually what we've done here is we've actually got a matte sealant over it, so that you can actually use it, which makes it waterproof, and you can actually use it next to sinks, so that the sealant will allow water not to seep into it. And then, of course, locally, these are two award-winning houses by local Canberra architects, where we see different uses of concrete block. Nowadays, concrete block come in different colors. So this is a small block, probably call this a brick. And here you can see that we have a hammered finish to the colored concrete block, which makes it a lot more rustic and a lot more palatable to the everyday taste, if you like, which is not quite as challenging as this sort of exposed concrete block, which I prefer, by the way, the exposed concrete block, that is, of course. Are there any questions? All clear? No one need to know anything else? Like, a sensible question would be, what are you going to put in the exam? No? No one want to know? All right, never mind. It'll be a surprise for you then. Okay, so if there's no more questions, then I think we'll wrap up the lecture for today. This is also my last lecture. This fourth lecture on materials is my last lecture. So thank you all very much. It's been a pleasure.